Hello, hello. Okay, so any questions before we get started? So we enter in the third week of the semester, right? So the first midterm will come in how many weeks? 3 weeks? 3 weeks, right? That means actually next week you will be able to reserve your spot. Okay, so clock is ticking. All right. So to prepare your midterm one, okay, make sure you find your study partner. Okay, don't do this alone. It's more fun when you actually have someone to talk to. Okay. And everybody has your calculator, right? Have you become a good friend with your calculator now? I hope it does. Okay. I hope you have been doing that. Okay. So just share with you that how difficult it is for a student to keep yourself concentrated. Okay. So in the first lectures, I say one thing I observed in the past 10 years is that mass majority of students will focus on the course materials in the first week. Okay. And then it decays. So how fast do you think the decay will be? So if you look at the number of students who watch the in-person lecture videos on YouTube, it's actually very clear. Okay, so for the first recorded in-person lectures, we have around 400 students who already watched the video. Okay, so that's the first video. Then let's look at after a week. Okay, the number dropped down to around 150. Okay, going from around 400 just a week, now become 150. When we enter the third week, it's 80. Do you see how fast we can actually get distracted? It's scary. Okay, however, the student doesn't have sense of that, right? But every time when I start to check, okay, how many students have watched the video, right? I feel scary. Not disappointing. It's kind of like it doesn't really matter to me, right? It's not my life. I don't really care like how you do. I do care how you do your things, okay, but it doesn't actually change how I perform, right? It doesn't really matter to me, right? You are not my really biological kids, right? If you're my kids, you're doing that, you'll be in trouble. Okay. But on the other side, I understand that okay, many of the students are actually busy. Okay, so I encounter so many students who will come to my office hour and explain to me about his or her specific situation. Okay. And there's actually one kind of person that I always talk to them because they will say, hey, Dr. Chen, I need to work. Okay. I don't have time. This becomes actually a very interesting question I encounter every year. I heard this question all the time, right? So I always say, I appreciate that your effort trying to take these courses, but the things that really matter is not that you take these courses, but you pass this course with the grade that you want, right? Otherwise, what's the point of taking this course? Okay, so then I tell them, okay, yes, I know you're busy. That's why you need to be more efficient. You need to be better planned. Okay, so a student, one thing I feel like the student need to actually do much better is actually to plan your life. Okay, so in the first lecture, I say I treat everybody as adults. I really do. Okay, but when I say I treat as adults, meaning that I expect you to be responsible for whatever you do to yourself. Is that fair? Yeah, so that's all I hope for, right? And my role is really just trying to be helpful, trying to get the things that you want. Okay. So I don't think actually that many professors care about you. They are so busy, right? I'm very busy too. Yeah, but I do care about my students. Okay, if you actually in my sections, email me, I will definitely reply to you. I won't ignore you, right? Because I feel like you decide to take my course, you want to follow my lead, then I'll do my best for you. Okay, so no matter who you are, I will say, yes, let's connect. Yes, let's do this together. Yes, use me as a resource. Okay? But at the end of the day, you are the only one who can decide what can potentially happen to your life. Okay, so if you're actually you are actually working and then taking this course, then work with me early. Let's make it work. Let's get the things that you want. But at the same time, you know it's not going to be easy. You know you have to put in effort. Okay, but you're not doing this alone. Okay, I'm here with you. So don't just fall off the train so quickly. Okay, stay with me. Okay, don't fall behind. Okay, really understand what I say in the in-person lectures. Most of the time, that's actually sufficient for you to get the grade that you want. All right? So what we're going to do this week is that we're going to finish chapter 11. Okay, so last week we started to tell you about the definition of reaction rate. Okay, so basically is how the concentration change over time, right? And depending on you are reacting on product, for the reactant, we actually monitor the disappearance rate or consumption rate of the reactant, or the formation rate of the product, right? To make the rate the same across the board, then you actually normalize all those quantities by the coefficient inside your chemical reaction. Okay, so that's what we actually go through last week. Okay, so and we also tell you the reaction orders, right? So every time we write out the reaction rate of a reaction, on the left-hand side is always rate. On the right-hand side, you're going to write the rate constant K times your reactant to certain power. Okay, so that question mark indicates the order of the reaction. Okay, so you can have multiple reactions, then each reactant will have its own orders. But the overall reaction order will be the sum of all those exponents or all those powers, right? Those are the things that we talked about last week. Okay. So this type of equation, we call it as the differential rate laws. Okay. And what we are going to do today is going to tell you this thing is called the integrated rate law. Okay. So the main difference between the two is actually the integrated rate law allows you to calculate the remaining concentration either for your reactant or product, okay, at any given time. Okay. So the main difference between the differential rate law and then the integrated rate law is that in the integrated rate law, time appears. Okay, so you're going to have t, time, the variables inside your equation. For the differential rate law, you only actually know how the rate is associated with the power of the reactant. Okay, so that's the main difference between the two. Okay. That being said, that means when you actually read the questions, when you see the information about time, for example, after certain minutes, certain seconds, right? Those are the keyword tells you that you need to actually use the equation for the integrated rate law. Okay. In contrast, if you see, I want to know the orders of a reaction, they will be for the differential rate law. Okay, so some simple but very effective terms that allow you to differentiate which equation that you should use. Okay. So after that, then we'll talk about how the scientists figure out the reaction mechanism from the reaction rates. Okay, and that's the time we're going to introduce the concept called the elementary steps. Okay, So elementary step is actually just a simple mechanism coming out from scientist's mind. Okay, so I do some experiments. I observe certain rate. Okay, then I start to using my knowledge to propose some mechanism. Okay, the beauty of that proposed mechanism is that, well, since it's actually proposed, right? Therefore, you can actually derive the corresponding red laws step by step. Okay, so what scientists do is actually, okay, I create a mechanism, I can derive the red law, and then I can compare the red law to the experimental red law. If they are consistent, then the scientists will say the proposed mechanism at least, okay, satisfactorily describe the behavior of what I observed experimentally. Okay, so most of the time, the scientists will actually propose a mechanism that doesn't really work. They know then there's a time that we know we actually revise the mechanism. Okay, until that our proposed red law agree with the experimental one. Okay, so that's actually a big part of chapter 11 is asking you, okay, I do the experiment, I observe these red laws. Okay, then which of the proposed mechanism is correct? Okay, so those are the things we're going to practice today. The very last topic of chapter 11 is called the Arrhenius equation. Okay, so the name doesn't really matter. The concept is the things that matters. Okay, so every time we talk about this reaction rate, okay, every time we talk about rate for the chemical reactions, there's actually a term you must heard before called the activation energy. Okay, so idea is actually very simple. No matter what we want to do, okay, for the reaction, there's always an energy barrier that your reaction needs to actually get over, then the things can move forward. Okay, so the Arrhenius equation is actually an equation that describes how the activation energy is related to the reaction rate. Okay, so those are all the things we need to learn for this chapter. Okay, so everything will actually connect with each other. Okay, but I give you a kind of 5-minute summary about what chapter 11 is actually about. Okay, so any questions before I head into the main content? Right. So first thing first, we need to actually finish all the differential rate law questions. Okay, so the most important type of questions for differential rate law is that every time I write out this, okay, reaction rate equals the rate constant K equals times your reactant, okay, not product, but reactant to certain power. Okay, so that's the format that you always want to have when you see this, when the question is asking you, okay, what's the order of the reaction? Okay. The typical questions will look like this. This is actually the most typical question you're going to encounter for chapter 11. Okay, so we're going to see a big tables, and inside the tables, you have the a lot of numbers. Okay, so if you look at these tables, first, it actually tells you what the reaction that you have, right? So this question says, given the data below for the reaction 2A plus 2B plus 4C, they give you D plus E plus BF. Okay, and it says the reaction is X1 order in A, X2 order in B, X3 order in C, and X4 order overall. Then I want you to explain, I want you to solve what's X1, X2, X3, and X4. Then we got a big table like this. Okay, so how do you actually solve a question like this? Okay. So one thing I want to point out is that inside these questions, do you see the keyword order keep appearing, right? is x1 order in A, x2 order in B, x3 order in C, x4 order overall, right? Every time you see that order, what it means actually, it must associate with your differential rate law. Okay, so how to actually write out the rate law for, how to write out the differential rate law for this specific reaction? First, you need to know, you must start from the rate on the left, right? The rate is going to equal to a rate constant K times, in this specific case, it will be your reactant concentration to certain power, right? So it will be A to the x1 power, B to the x2 power, C to the x3 power. And then your x4 is simply equals to x1 plus x2 plus x3. Okay, let's the overall, right? When we say overall, it's actually sum of all the orders of all your reactants. Okay, any questions for this? So here I want to emphasize that when you write out the differential rate law, you should notice that I only put A, B, and C, right? I did not put D, E, F, right? So you need to actually remember every time when you write out the differential rate law, the concentration term must be the concentration term of your reactant. Okay, only reactant, not your product, not your intermediate, not your catalyst, only your reactant. Okay, make sure you know that. Okay, so once you have this is actually the most important step. Okay, you must be able to do this. Okay, so if I give you a chemical reactions, you must know what's actually a general forms of the differential rate law of that specific reaction. Okay, you will always have the rate on the left. On the right, you have K, rate constant K, times reactant to certain power. Okay. So once you know this, then you can actually start to look into the tables. So inside the table, you're going to see a few columns. Okay. These three columns. Okay. These three columns, you can see that, let's say it's the initial concentration of A, initial concentration of B, initial concentration of C, right? So those are the information for your, again, for your reactant. All right. And then you have another column specify the initial rate, right? That's actually the information for your rate. Then you're going to have 1, 2, 3, 4. 4 rows, right? 4 rows means actually if I change the concentration of one of my reactants, how the rate is going to change accordingly. Okay, so the way you handle this question is actually you're going to use these things to write. Okay, so from the first data set, you can write the rate is going to equals to let me rewrite the general form here. Okay, so this is actually the general form, right? So from the first row, we know the rate is 2 times 10 to the negative third equals to rate constant K times concentration for A is 0.1 to the x1 power, B is 0.2 to the x2 power, C is 0.4 x3 power. Okay, you will need to be able to translate the general equation, put in the numbers at the correct position. Okay, so let's actually from 1, right? 2, it will be 2 times 10 to the negative 3 equals to K times 0.2 to the x1, 0.2 to the x2, 0.4 to the x3. Okay, so this is actually a second one. Would you be able to actually write this in for the third and fourth equation yourself? It should be actually very straightforward, right? But make sure you can do this. 4 times 10 to the negative 3, rate constant k times 0.3 x1, 0.4 x2, 0.4 x3. The very last one will be 1.5 times 10 to the negative 3 equals to k times 0.4 x1, 0.6 x2, 0.4, 0.2 x3. Okay, so if you can just write these things out, then the things you need to do after this will be, I need to use these equations. There are 4 equations. I want to solve my x1, x2, x3, and k. Okay, you have 4 equations, 4 variables, so this is actually definitely a solvable condition. Okay, so how do you actually solve this effectively? So the things you need to do is actually do the equation operation. Okay, the whole equation operation. If I define this is my equation 1, 2, 3, and 4. Let's say I want to solve my x1. Okay, so what I'm going to do will be, I'm going to use equation 2 divided by my equation 1. Okay, so if you do this equation operation, okay, so equation 2 divided by the equation 1, on the left-hand side will be 2 times 10 to the negative 3 divided by 2 times 10 to the negative 3, right? But divide this by that. Since they are the same, therefore, we know on the left-hand side, all you get is actually 1. Okay? On the right-hand side, k divided by k, you got a value of 1. The first term, 0.2 divided by 0.1. So these things is equivalent to okay, so I want everybody actually see these things very clearly. Okay, make sure you know this. When we do this row by row operation for the, if the exponent is the same, then it will be just this number divided by itself. Okay, that means actually this whole thing will become just 2 to the x1 power. Okay, so I will just write here 1 equals to 1 times 2 to the x1 power. Okay. How about this term? 0.2 to the x2 power divided by 0.2 to the x2 power. 1, right? They are the same number. Therefore, you know the third term is 1. And the fourth term will be 0.4 to the x3 power divided by 0.4 to the x3 power. Therefore, it's also equals to 1. Okay, so once you choose 1 and 2, you do the division for the whole equation, then you realize that the variable k, the variable x2, variable x3, they all got canceled out, right? So that you actually compare to a very simple equation. 2 to the x1 power equals to 1. Therefore, you know your x1 has to be 0th order, right? So this is actually the things that you need to actually have a good eye now. Because from this simple example, you see that Let's say I want to solve x1. That means I want to keep all other concentration, meaning for my B or my C, if they are the same, then the x2 and x3 doesn't really matter. Everybody follow what I just said? Okay, so what you're trying to see is actually, you only want to actually, when you pick up two equations, you want to pick these two equations, they only have one concentration, they are different, but the others are the same. Then you can actually solve the power for, let's say, specific reactant, right? So in this case, equation 2 and equation 1, you can see that the only difference between these two equations is the concentration of your A. But B and C, they are the same, right? That means actually after you do this equation-wise division, whatever exponent or whatever power associated with your B, associated with C, they are going to be canceled out. So it doesn't really matter anymore. Okay. And then by doing this, quickly you turn this 4-variable equation into 1-variable equation, which you'll be able to solve that really quickly. All right. So let's actually the main trick that you need to actually be really good at. Okay. So once you know this, then you suddenly can see that the x1 right now, you know, is actually 0, 0, 0, 0. Okay. Then you decide which one you'll solve afterwards. Let's say you want to actually solve your x2, right? Then you're going to do the same operation, but you want to actually keep your C the same. Okay, so when they pick two equations where the C concentration is the same, but the B concentration is different, then you will be able to solve your x2. Okay, so with that being said, I can pick these two, right? The concentration of the C is 0.4. But for the B, one is actually 0.4, one is actually 0.2. So up to this point, I don't really care about the concentration of A anymore because I know the power of A already. Right, so what you're going to do will be, let's do equation 3 over equation 2. Okay, so 3 over 2 on the left will equals to 2. K over K still give you 1. Okay, and then 0.3 divided by 0.2, that is 1.5 raised to the 0th power. And then you're going to have 0.4 divided by 0.2, which give you value of 2 raised to the x2 power. And the very last one, 0.4 to the x3 divided by 0.4 to the x3, again, they give you a value of 1. Okay, so once you see this, then you can actually see this 2 to the x2 power is going to equals to, this is equals to 1, right? So this whole thing will equals to 2. Therefore, you know your x2 will equals to 1, right? 2 to the first power will give you a value of 2. Okay, so this is actually how you solve your x2. Okay, everybody still follow? Any questions? Yeah, you can just put it back because once you have the exponent overlay, you can actually calculate a number directly. Yeah, then it becomes just numerical calculations. It's very simple. Okay, so any other questions? Yes. No, you can do it randomly. It's fine, right? But the reason I present this way is it's easier for you to follow. Okay, but it doesn't really matter which equation you used for the first place, right? It really depending on like which one you want to just solve first. Okay, so once you actually know this, then right now you can actually put these things back, right? Because you now know your x2 is always first power. Okay? So to solve for your x3, the only thing you need is actually, you just pick two equations where your x3, they are different. Okay? So I will pick these two then. Okay, I'm going to pick equation 3 and equation 4, right? Because that's actually the only two. This is actually the one that shows different concentration in your C, right? Of course, you can also pick equation 4 to equation 2. That's fine too, right? Because concentration of C, they are just different. Okay, so I'm going to do, let's say I do equation 4 and equation 3. Okay, so when I do this operation, then I will take a look. Okay, so equation 4, you have C of 0.2. Equation 3 have C of 0.4, right? What I will do is that I will do this larger number divided by the small number. It's easier to actually do your mental calculation, right? So I will do equation 3 over equation 4. Okay, on the left-hand side, it will be 4 over 1.5. K divided by K, they give you a value of 1. Okay, and then it will be 0.3 over 0.4 to the 0th power. And then 0.4 over 0.6 to the 1st power. And then the very last one will be 2 to the x3 power. Okay? So this thing will give you 1, right? Because no matter what number you have, when you raise to the 0th power, you always get a value of 1. Okay? What would this give you? This 2/3, right? Okay, so what do? You multiply 3 on both sides and then divide it 2 on both sides, right? So therefore this and that will cancel out. This will give you 0.5. This will give you 2. That will give you a value of 4. Therefore, 2 to the x3 power equals to 4. Therefore, x3 equals to 2. Everybody follow? Okay? You can actually do this calculation using your calculator. Okay? But it's simple enough that you should be able to actually see these things directly. Okay? So up to this point, you should see that it is your x1 order is actually 0th order. X2 is actually 1st order. X3 is 2nd order. Your x4, which is the sum of all the order, right? Its overall order is just 0 plus 1 plus 2, which will give you the overall order of 3. Okay, so let's actually how you address these questions. Okay, so any question for this? It's very standard. Okay, very standard type of questions, but you must learn how to do these things quickly. Okay, any question for this? Yes. 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 That's actually the things I want to think after this. Okay, so even though it did not ask you the K, but it could. Okay, and in some of your homework quiz and midterm, it does. Okay, so the things you do is actually, since you know the order, right? What you do is actually pick any of the equation. It's all the same. For example, you pick equation number 1. You write 2 times 10 to the negative 3 equals rate constant K times 0.1 to the 0th order, 0.2 to the 1st order, 0.4 to the 2nd order. Okay, so once you have this, you can see that you only have one unknown, which is your K. right? Then you use your calculator to figure out the value of k. Okay, and there'll be actually complete questions they can ask you because there's only 4 variables here. Actually 5 because x4 is actually sum of x1, x2, x3. But that's all you need to know for this type of questions. Okay, so very standard type of differential rate law questions. Okay, I hope you know how to solve these things in the in-person lecture already. Okay, then when we go back home, you will just repeat the same process. All right, is that clear? Any questions? Okay, we're good. Okay, so once we finish this, the other things that is actually interesting is this. This is actually still associated with this differential rate law, but it focuses more on the unit of k, okay, the rate constant. All right, so the unit of k changes depending on the overall reaction orders, okay? But somehow like the chemistry department want to test you this concept, okay? So let's just go through some really simple stock practice. Okay, let's say you have a differential rate law like this. Okay, so what's the order of this reaction? Zeroth order. Okay, so every time we say the order is always the power of your reactant. Okay, so here is actually 0th order, right? What's the unit of the k here? The rate, what's the unit of your rate? Yes, molarity per second. Okay, because the rate is actually how the concentration changes over time, right? Therefore, you know, regardless the order of the reaction, the rate always have a unit of molarity per second or per time. Okay, sometimes they use minutes. Okay, so concentration per second for 0th order, right? And then here, if it's 0th order, this is just simply equals to 1, right? It doesn't change the unit at all. Therefore, for the 0th order, the K is going to have the unit molarity per second. Okay? What if it is 1st order? That means this becomes 1, right? So if let is 1, that means actually the unit of your K multiply the molarity to the 1st power. That's what it means, right? And then it must have eventually get to this molarity per second because that's actually unit of your rate. And you have equal sign, that means actually the unit has to equal on both sides, right? So this means if it's actually 1st order, you divide the molarity on both sides, right? Then the K for the 1st order will have unit of per second. Everybody follow this? Okay. So now let's move to the 2nd order. This will be molarity to the 2nd power, right? Therefore, you know the unit of K for the 2nd order will equals to 1 over per second per molarity, right? There will be actually a unit of your 2nd order. Okay? Of course, you can just generalize all these things. Okay, so you can do this for any orders that you want, following the same logic here. Okay, but the general equation is that the unit of K is going to equals to molarity 1 minus N per second. Okay, N is just the order of the overall reaction. Okay, if it's zeroth order, then you have a molarity per second. First order per second. Second orders per second per molarity. Okay, so this is actually the general form. If you want to actually memorize this, this will be a quick way to figure out the unit of K. Okay, but you will ask, why do I care? Right? Why do I care? The things that you want to know this is actually very simple, because sometimes you can just look at the unit and you will know what's the reaction order. Okay, so the reason we want to actually bring this out is because in many of your homework or in many of your quiz, it won't tell you the order directly. Instead, it just say, okay, you have a rate constant. It's a certain number, okay, per second per molarity. And then start to actually calculate things afterwards, right? But knowing the order is critically important, especially when actually heading to the integrated rate law. So this is actually why I want to actually spend some time to tell you, if you can see the unit of your K, you should be able to actually extract out what's the reaction order. Okay, so that's actually something that we need to actually practice for this translate. Okay, it's actually very simple things, but it's if you can actually do that, then that's actually wonderful. Okay. So that's pretty much all the things that you need to know for. And that's all the things that you need to know for the differential rate law. We need to actually move to the integrated rate law. Okay, so for the integrated rate law, the main difference is that time become a very important variable, okay, in your question and in your calculations. In CHEM1312, there are 3 integrated rate law you need to actually memorize, okay, which I summarize here. For this type of integrated rate law, the reaction always has this AA to form the product. The reason that is important is because this actually tells you for the integrated rate law you are going to memorize, it's actually a single reactant reaction. Because you only have A, right? You don't have other species. Okay, so it's a single reactant reaction. Okay. Then this is actually differential rate law that you just learned. Okay, so if you actually good at math, then you know the rate law is dA dt. Okay, how the concentration of A change over time. Okay, then you do the integration on both sides. Okay, then you integrate from time 0 to time t. Then you have this. Here, I would strongly suggest that you memorize A t equals to negative kt plus A0. Okay, this will actually make it a lot more conceptually clear. Okay, what is AT? What is AT? Concentration of A at time t. Okay, the concentration at a specified time. Okay, that's AT. What's A0? The starting concentration of A. Okay, so it's very important that you see the differences. AT and A0 are 2 different things. Okay, the T specify the condition of A at that specific moment. Okay, there is actually remaining. Okay, make sure you know. Remaining, okay, the things that you still have. Okay, remaining A at time t. Okay, if you have zeroth order, then the concentration of A at time t and time 0 can be related to this simple equation, negative KT plus A0. Okay, so one thing the textbook wants you to learn is that if you understand, if you memorize the equation, okay, if you plot out your AT over T, what would you expect? Yeah, so if you do this, right, this can be simplified as y equals to negative kx plus c. Right, if you say the t is actually your x-axis, your a or a at time t is your y. This actually goes back down to a very simple linear equation, right? Y equals to ax plus b. Right, so you know it has to be a linear relationship. Okay, it's linear, right? What's the slope? Negative k, right? So it will be something like this. It is a straight line, right? Linear line. Okay, slope will equals to negative k, right? What's the intercept at the y-axis? This point will be your initial concentration, right? Can you actually translate the equation into the plot I just draw? Okay, you will need to do that. Okay, that's the things you will be asked as well. Okay, this actually tells us what? If today you plot out your A, which is your concentration of your reactant, over time, if you see a linear relationship, okay, with a slope that's negative, that tells you that specific reaction you're actually reading is a zeroth order reaction. Okay, so that's the things why this is actually so important. That's the things that you need to memorize. That's the things you need to actually comprehend. Is that clear? Okay, so we're going to apply the same thing for the first order and the second order. Again, differential rate law of first order reaction, right? Because this is one, right? So you know that's actually first order reaction. Then you replace your rate with dA over dt. Then you do your integration by moving the concentration around. This is actually the solution you're going to get for the integrated rate law. Okay, natural log A equals to negative KT plus natural log A0. Okay, so it is actually very similar to the things that we say here, right? AT equals to negative KT plus A0. Here is actually natural log AT equals to negative KT plus negative A0. Okay? So if today, again, I want to draw a plot, right? Where your x-axis is still t. But here, the y-axis, you're going to plot out natural log AT, right? If you plot out natural log AT over t, what are you going to get? It's again a linear relationship, right? Just like right now, the y is natural log A. Okay, so you still get something like this. Okay, and then again, the slope will be negative k, but the intercept will be natural log A0. Okay? So this actually tells us what? Tell us if today, if you are given a figures, okay, where the y-axis is natural log AT, your x-axis is time, and show this linear relationship, then you know that reaction will be first order. Okay, so let's the translate you must become very good at. Is that clear? Okay, so I guess by now, you should see the same pattern here. For the second order, it will be 1 over AT equals to KT plus 1 over A0, right? So the plot you're actually trying to say will be, again, your x-axis still T. But right now, your y-axis will be 1 over AT. Okay, the only difference is here is that the slope right now becomes positive, right? So you're going to see something like that, where the slope is still okay, but the intercept will be 1 over A0. Okay, so once we understand this, okay, then when you actually go back and look at your quiz, you're going to see a question like this. It's going to give you like a couple plots, okay, and one of them is going to show the linear relationship, okay, and ask you, okay, which one follows first order reaction. Okay, and then the one you can actually to assign will be your y-axis will be natural log AT. Okay, so if you're actually looking for the second order, then the y-axis you're looking for is 1 over AT. That shows the linear positive slope, linear line. Okay, so those are the things that you need to be able to comprehend by yourself. But this is actually kind of the three equations that we need to actually memorize. Again, zeroth order, AT equals to negative KT plus A0. First order, natural log AT equals to negative KT plus negative natural log A0. Second order, 1 over AT equals to KT plus 1 over A0. Okay, so these are the three equations that we must memorize. Okay? So, if we can all understand this, okay, then we can just start to solve some more complicated questions. Okay, so this question says the reaction AB becoming A plus B has a rate law which the rate equals to, sorry, this should be a rate constant K times AB to the second power. Calculate the rate constant in liters per mole per second. It takes 120 seconds to reach an AB of 0.2 mole per liter from the initial concentration of 0.8. How many of you know how to solve this question right away? That's quick. Okay, that's good. Okay, but I want to actually go through this logic together with you so you can just see how easy you can actually find out the proper way to solve this. Okay, start from the keywords. What's the keyword here? Not the rate constant, not the rate law, not the initial concentration. What's the main difference between the differential rate law and the integrated rate law? Time. Do you see that time information? That is the key. Why that is the key? Because you see the time, you know it must be one of the three. Simple, right? We went through three equations just 2 minutes ago. We come back to here, right? How do you know you need to actually use one of those three equations? It's because that time information, because only integrated relay have the information of time. Okay, so (120) is the things that tells you this must be the integrated relay, right? So you have the zeroth order, first order, and second order. Which one should you pick? Second order, right? Because it says this, right? So you know it's actually second order. Therefore, you already know the equation you want to use will be 1 over AT equals to KT plus 1 over A0. You know that's the equation you're going to use. Very simple, right? Okay. So once you have all these things went through in your mind, okay, I don't know, if you really know how to do this, you see this, you actually immediately know what you need to do. Okay. Then you go back to do our QD pack, right? What's the things you need to solve? What's the Q they want you to solve? Rate constant, right? Which is your K. Okay, so you need to solve your K. What's the data that you have? Initial concentration, which is A0, right? They give you 0.8 moles per liter, right? And then at 120 seconds, so T equals to 120 seconds, right? The concentration is 0.2 moles per liter. Okay, anything else? That's all, right? Therefore, write out the equation. Do you have your AT? You do, right? AT is 0.2, right? Therefore, it's 1 over 0.2. Rate constant that you don't know. Time is 120 seconds. Your original concentration is actually 0.8. Once you write it out, you realize that's the equation I can actually use to solve my K. Okay, so if you do that calculations using your calculators, you should be able to get the K is going to equals to 3.75 seconds. There's not second. 3.75. That's what's the unit? Right? That's the per molarity per second. However, yeah, let me see it. See, calculate rate constant in not 3.75, 3.75 divided by 120. I realized this is actually 5. That's actually 1.25. So 5 minus 1.25 gives you 3.75 divided by 120. Therefore, the final value will be 0.031 per molarity per second. So that will be the answer. Okay. Okay, so I hope you see that every time we read the questions, in order to actually answer these things quickly, efficiently, and correctly, you must know there will be actually a specific equation that you need to use. Okay? So you need to know what's the keyword here. Because once you know the keyword, then you know you must do the integrated red law. Okay? This question can actually get even more complicated if I don't provide that differential red law for you. But you'll come to the same conclusion. The reason is because remember I said the unit of k matters, right? So if today I don't give you that rate equal to k times AB to the second power, you should still be able to actually solve this, because if you look at the unit of your k, then you should actually come to a conclusion that this has to be a second order reaction. Okay, once you know that, then all the things, subsequent operation will be the same. Okay, so this questions, the original question is actually a easier format for this type of questions, but it can be further complicated by removing the differential red law for you. Instead, they provide you the unit of k. Okay, that's why I say it's important to know the unit of k, because once you know the unit of k, you will know the order of your reaction. Okay, so I think that's actually pretty much the variance that you will be tested. Okay. Okay, so now let's look at the other one. In a first order decomposition in which the rate constant is 0.5 per second, how long will it take in minutes until 1.6 mole of the compound is left if there was 4 mole per liter at the start? What's the key words? Okay, I hope you start to see this, right? How long it take? Okay, ask you about the time, right? Every time you see if a question is asking about the time, and then it's related to the reaction rate, you must actually looking for the integrated red law. Okay. So now we know we are looking for the integrated red law, right? But what's the reaction order? This says in a first order, right? In a first order decomposition. Okay, so this is actually the simpler version, right? I tell you it's order already, right? But if today I did not say this to you, if I say in a decomposition reaction, okay, in which the rate constant is 0.5 per second. Okay, can you see that if you have unit per second, it's first order. Okay, so the general equation is unit has this molarity 1 minus n times this, right? That's actually a unit of k equation. For the first order, it's m to the 1 minus 1, m to the 0th power. Then you have the unit of per second. Okay, so if you look at the unit, you must know it's first order. Okay? So right now, if we know it's first order, therefore you know the equation you're going to use is natural log AT equals to negative KT plus natural log A0, right? So that will be the equation that you're going to use. Okay, once you actually got to this point, then you know you'll be a piece of cake. Okay, then go back to the equation, go back to the questions and start to see what's the Q? How long, right? So you're solving for T. Okay. Data. your A0 is going to equals to 4m. Your AT is going to equals to 1.6 m after t in seconds. And then your k equals to 0.5 per second. Right? That's all the information that you get from this specific questions. Okay? So once you have all this information listed, then just go back to your equation. Okay, AT is 1.6 equals to K is 0.5. T is actually the things you want to solve. Your A0 is 4. Okay? Then you use your calculator to calculate all these numbers. So your 0.5t is going to equals to natural log 4 minus natural log 1.6. Okay, so this will equals to 0.91629. Therefore, your t is going to equals to 1.8326 seconds. Okay, so here the unit of your t will be actually the reciprocal unit of your k. Okay, since your k has a unit of per second, therefore the t has a unit of second. However, in these specific questions, it says they want to know the time in minutes. Therefore, it's going to equals to 1.8326 divided by 60. They'll give you 0.031 minutes. Okay? So let's actually how you address this kind of questions. Okay. So integrated rate law is actually things that it's actually very easy to identify, right? As long as you have the sense that if I see a question that have time information in it, it has to be integrated rate law. Okay, but you have to actually make sure you are sensitive enough to detect that keyword. All right. The other things that chemistry department trying to trick you is that the AT, okay, the concentration of A at time T, that's actually the remaining A. Okay, so what do I mean here? I want to actually pay attention to this. How long will it take in minutes until 1.6 m of the compound is left? Okay, so left is equivalent to remain. Okay. In the at time T, you still have how many of A, right? But sometimes when you see these trickier questions, you will say, okay, you say 1.6 of A is consumed. What it means is that, okay, A is going to be decomposed. The decomposed one, if it says it's consumed, that means actually decomposed one is 1.6 m. Does everybody follow the things I just say? That means actually the remain one is 4 minus 1.6, which is you have left much remain. Okay, so once you actually know 2.4 is actually the remaining one, then when you plug in here, 2.4 is actually the remaining one, 4 minus 1.6 is 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 4 minus 1. this will be actually your A times T. Okay, so the wording matters a lot. Okay, you need to make sure that you know the AT is actually concentration of A times T. Okay, either you will see that the word used left, remained, sustained. Okay, they all indicate the same thing. That's actually the A that you want to have. If it says consumed, it's the opposite. Okay, so you want to first calculate how much is remains so you can just plug into the equation that you memorize. Is that clear? So those are the tricky part of this type of questions. Okay. All right. So with that being said, then we can actually enter the very last things we want to talk about. The reaction mechanism. Okay, so for the reaction mechanism, we need to actually understand a few keywords. Okay, one is called the elementary step. One is called the rate limiting step. Okay, so you need to actually memorize all this elementary step was coming from proposal. Okay, scientists actually propose the reaction actually happen, follow this step A, step B, step C, and step D. Okay, so one beauty of all this proposal is that all this equation we write out is defined, right? So what you're trying to do is actually, I have a model. Okay, I give the model a specific rate. Okay, and then to happen in a specific way. Then I can actually derive what is actually corresponding rate law I should actually observe. Okay, so every time we write the elementary step, you will write out the corresponding rate law directly. Okay, so this is actually very different from the rate law we talk about, the differential rate law we just went through in the beginning of the class, right? You need to actually do the experiment, have all different conditions. They compare condition by condition to figure out the orders. Okay, so you can actually use the coefficient in the equation to write out your rate law in those conditions. However, for the reaction mechanism, right, you propose the reaction pathway. Okay, so when scientists propose those pathway, you write out the simplest way they can actually interact. Therefore, we can actually write out the rate law of those elementary steps based on the mechanism you propose. Okay, so that's actually a big difference between the two. Okay, and then the other very important thing that you need to actually know that you want to always find out the rate limiting step. Okay, because since that's actually a step, let's say you have 100 steps for your overall reaction. Okay, but let's actually step significantly slower than the others, right? Then all your reaction will actually stuck and then rate limiting step. Okay, and then this slowness allow you to actually write out the concentration reactions between your reactant and product, which will be the equilibrium constant K. Okay, so scientists can combine all these things to decide who is actually the correct reaction mechanism. Okay, so we're going to go through all these details, how you can actually see this, and then to justify, okay, I compare the derived rate law to the experimental rate law, you will know who is actually correct and who is not. Okay, so we'll do this on Thursday, and we'll stop here today. Thank you.